All right, so now that we understand the conditioning of problems, let's talk about stability of algorithms. So the idea is we're dealing with some function, and given any function, we can tell whether that function is well conditioned or not using the formulas we saw in the previous section for condition numbers. But suppose that function is well conditioned. It's still possible that whenever we implement that function in a computer program, um, that it could still give us a bad answer. Because what happens when we implement functions in a computer is it doesn't just do the function analytically. In a lot of cases, it gives us a decimal approximation to the function. All right, so whenever we evaluate a function in a computer, what the computer is doing is it's running some algorithm that approximates the function. Like maybe it uses the Taylor series, or maybe if we're trying to do the derivative of a function, it uses the difference quotient to give us an approximation to the function. Whatever that algorithm may be, uh, the computer runs that algorithm and gives you a decimal answer for your result. All right. So then the question is, whenever I get this decimal answer, is that decimal answer accurate? You would hope that if a function is well conditioned, that your algorithm would give you a good answer. But the idea of stability of algorithms is that suppose we have a well conditioned problem, it's still possible that the algorithm that you're implementing has some issues, some things in it that can throw your answer off. Okay, so an algorithm that achieves the level of accuracy defined by the conditioning of the problem is a stable algorithm. But then one that gets unnecessarily inaccurate is called unstable. All right, so in this section, our focus shifts away from the function itself and whether it's a well-conditioned function, and now our focus is on what's happening inside our algorithm. So for example, if our function was the cosine function, this function is well conditioned. We can find the condition number for this function, and it's going to be a well conditioned function. But suppose your algorithm for evaluating the cosine function involves maybe a Taylor series, because if I ask you to do something like f of say pi over 4, we know how to do this analytically. If we know our unit circle and think about the cosine function for a second, we know that the exact answer is root 2 over 2. But a computer, when it evaluates cosine of pi over 4, typically what it's doing is it's getting a decimal approximation to cosine of pi over 4. It's not telling you exactly what the answer is, it's giving you some decimal number. And that decimal number is coming from some algorithm. Maybe, again, the algorithm is the Taylor series. So then we need to think about whether or not the Taylor series is a stable algorithm. Is it going to give us a good answer? One of the examples that we'll see in this section will show us that with the function e to the x, if we use the Taylor series to approximate e to the x, then there are some cases where we might run into issues. All right, so the idea here again is we're dealing with a function that's well conditioned, but we want to know, does the algorithm that the computer is using to evaluate the function, is it stable? Or is there some line in the code somewhere that could throw your answer off in certain situations? All right, so this is what we'll look at in more detail with the next few slides. So suppose we have an algorithm and we want to analyze how stable it is. One thing we can do is called a rounding error analysis. So the example they give in the book, example 6.2.1, the setup here is they're going to do a rounding error analysis in two different ways. One's called a forward error analysis, the other's called a backward error analysis. So what we're dealing with is we have two real numbers, x and y. Those two numbers may not be floating point numbers, but suppose we round them to be floating point numbers. Okay, so remember, a floating point number is a number that can be represented precisely or exactly using floating point representation. All right, so x and y, we round them to be floating point numbers. We'll call those rounded numbers round x and round y. And let's say that the machine precision that we're dealing with is epsilon. Just as a reminder, if we're dealing with a single precision machine, then epsilon is 2 to the negative 23rd. And in double precision, epsilon is 2 to the negative 52. So if you look back in your book, the way we do floating point arithmetic, if I want to do look at the floating point result of adding x and y, then I'm doing round x plus round y, where if you look back on page 117, they tell you what we mean by this symbol with the plus and a circle around it. So there they say that a plus b, this is addition using floating point arithmetic. A plus b equals a plus b, the exact answer, times 1 plus delta. So in other words, when we do floating point arithmetic, if we add two numbers together, the answer is going to be close to the real answer, but it may be off by some factor delta, where delta is some number smaller, less than or equal to your machine precision. Okay, so here delta is less than or equal to epsilon. And something you'll see them say in the book is that if we have, if we're using round to nearest, then we can actually say that delta is less than or equal to epsilon over 2. But let's just leave it as epsilon for simplicity. All right, so we're doing this floating point arithmetic, round x plus round y. Now, since we rounded x, then already we're dealing not with just the number x, we're dealing with some number really close to x. X times 1 plus delta 1, where again delta 1 is less than or equal to epsilon. Same thing for round y. Round y, we're not dealing with the precise or exact number y, we're dealing with something that's really close to y, the rounded number that we get when we round y. And now we're going to do this floating point addition here, which again, by this definition that we have on page 117, when we add these two numbers together, you get the first number plus the second number multiplied by 1 plus delta, or in this case we'll call it delta 3 because we already used delta 1 and delta 2 on the previous line. So the idea here is if I'm using floating point addition to find the sum of these two numbers, my answer is not going to be precise, it's going to be just a little bit off, and how far off it is kind of depends on our machine precision, because all of these deltas again depend on or are related to our machine precision epsilon. So this is just the setup. Let's, on the next slide, on the next page, let's see what these two different types of error analysis look like. We'll look at the forward error analysis and the backward error analysis. Right, so let's look at one of our ways of doing the rounding error analysis for floating point addition. One of the two ways is called forward error analysis. That means we're going to compare the computed result to the exact solution. So here I'm showing you what the computed result looks like, the floating point addition of x and y. Just copying over the line that we had on the previous slide. If I do all the distributing, distribute x into the parentheses, distribute y into the parentheses, and then take this term on the far right and distribute as well, then we end up with this line here. X plus y plus x times all those deltas plus y times all those deltas. Now, since each of these deltas, each one is less than epsilon, so this is less than or equal to epsilon, this one's less than or equal to epsilon, then that means that delta 1 plus delta 3 is less than or equal to 2 epsilon. Same thing here, this is less than or equal to epsilon times epsilon, which is epsilon squared. Alright, so that's where this inequality comes from. We're replacing the deltas with epsilons and rewriting in terms of epsilon. Where again, remember epsilon represents our machine precision. This last line here, and showing the computation for the floating point addition of x and y. All we've done to get from the previous line to this one is both of these terms, x times the epsilon stuff plus y times the epsilon stuff is exactly the same in both of them. So we factor that out, and we're left with x plus y times the epsilon stuff. Okay, so floating point addition, whenever we add two numbers in a computer, how it differs or how it compares to the exact solution, we can kind of see it pretty clearly right here. The exact solution would be this, x plus y. But when you add two numbers in a computer, you don't just do x plus y. You have to take into account all the rounding that's been done. And as a reminder, we rounded x and y to begin with to make them floating point numbers. And then, after rounding x and y to make them floating point numbers, we did floating point addition to those rounded numbers. So x plus y by itself would be the exact result, but then this shows us how far off we are from that exact result. So if we wanted to look at the relative error of the floating point addition for x plus y, remember relative error, we look at the computed result minus the actual result divided by the true answer. Okay, so looking at the relative error, in the book they skip a few, I guess, explaining steps on where this inequality comes from. In particular, this piece right here, I suppose that comes from something called the triangle inequality, but you don't need to worry about that here. Really all you need to worry about is our relative error when we do floating point addition is less than or equal to this expression here. And the problem with this expression here is that if the things that we're adding are relatively close to each other but opposites, so like 1 and if x is 1 and y is negative 1.000, however many zeros you want, 1. then those two numbers are really, really close to each other but opposite. So when you add them, you're getting a number close to 0. So in other words, if x and y are close to being the same but opposites of each other, then you're getting a number close to 0 in the denominator. And if the thing in the denominator is close to 0, we know that's a problem. That makes our fraction, that can make our fraction infinitely large. So the moral of the story in all this forward error analysis, something we're going to have to be careful with in our computer algorithms is we need to look out for any steps in the process where we might be subtracting numbers that are really close to each other. So in general, floating point addition behaves well, but we'll see in an example 6.2.2 in the book that there are some cases where if we're subtracting numbers that are incredibly close to each other, then we could unnecessarily be introducing a whole bunch of round off error into our answer. So we may be dealing with a function that is well conditioned, but then after all these subtractions of numbers that are close to each other, so that this number in the denominator with our relative error is close to 0, that error can build up and cause issues in our algorithm. All right, so this is forward error analysis. The basic idea is we're taking the computed result, this floating point xy, so that was this line right here. This is our computed result, and comparing it to the actual answer, this x plus y. And in general, floating point addition works well, but when y is close to negative x, then the denominator is close to 0, and we could have problems. All right, on the next slide, I'll show you backward error analysis, and then we'll briefly discuss some of the other examples in the book. The second way we can do rounding error analysis is called backward error analysis. The idea here is that we're going to look at your final result, your computed value, and show that it's the exact solution to some nearby problem or some problem that's similar to the one you're trying to do. So here, what we're trying to do is just simply x plus y. But there's lots of rounding going on. We rounded x, we rounded y, and then we rounded their sum. This line at the top is again just a repeat of the line that we've had on the previous page and already explained where it came from. I copied that here because on our next line, the floating point sum of x and y, I just want to be able to show where this is coming from, and really all I'm doing is taking this 1 plus delta 3, that entire quantity is being distributed into the parentheses to those two terms inside the parentheses. So you have x times 1 plus delta 1 times 1 plus delta 3 plus y times 1 plus delta 1 times 1 plus delta 3. So again, this is the final result of doing addition in a computer. When you try to do x plus y, what you end up with is x times this delta stuff plus y times this delta stuff. Now, we saw in the previous slide that with forward error analysis, we could talk about where we might be introducing unnecessary round-off error if we're dealing with x and y's that are close to being opposites of each other. But here, if we do backward error analysis, all we're doing is we're just looking at our final result. Our final result is the exact sum of two numbers that are close to x and y. So in other words, this floating point addition of x plus y I'm getting some number out of this, and that number that I get out is this exact sum that I have written here in this line. This sum that I have written here is some number close to x plus some number close to y. And so this is an exact solution to something similar to doing x plus y. So we would call this floating point addition backward stable. Now, I know that this idea of forward error analysis and backward error analysis is kind of strange when you first see it. I know for me personally, I had to read and reread this section several times because even though I've seen it before, I had to just kind of pay attention to the details and try to make sense out of what the book is saying. But one of the goals of showing you this error analysis, the forward and the backward error analysis, is just to kind of give you a slight idea of what we mean with these two. Forward error analysis meaning we compare our computed result to the exact solution. Backward meaning that we look at our final solution and see, is it an exact solution, something similar to what we're trying to compute. These two ideas will show up in later chapters, and so even aside from the idea of stability of algorithms, it's good to kind of introduce the topics here so that when we do see this error analysis being mentioned in later chapters, we at least have a rough idea of what they're talking about. Okay, so if this seems kind of strange right now, that's okay. As we see more and more of it through the next few chapters, you'll get kind of more used to the terminology and what it's talking about. Alright, so I want to finish this lesson by just kind of summarizing the other two examples that they show you in the book. One is they're looking at the exponential function and showing how we could run into issues. The other, they're looking at numerical differentiation and some of the issues you run into if you use the difference quotient as an approximation to the derivative. Alright, so I'll have you guys read those yourselves, but I'll just kind of highlight a few key points from those two examples in the next slides. Alright, so what we're going to do next is we're going to look at example 622 in the book. This gives us an example of an unstable algorithm. Alright, so what we're going to do here, I'm not going to go through every line of the example, but you can read that on your own. I'm going to just point out a few interesting things that relate to this idea of stability of algorithms. So we're doing this function e to the x, and the way we're going to implement e to the x in the computer is with a Taylor series. Alright, so remember going back to our conversation at the, well, I say conversation, y'all aren't talking back to me, I guess, because we're on YouTube. But what I was saying earlier about the algorithms, you're not getting these analytic results. You're plugging some algorithm, you're running some algorithm in a computer and getting some decimal approximation. And so what we want to analyze here is whether or not this algorithm that we're using is stable. Now, I want you to look on page 127 at that MATLAB code. And one line that's going to be particularly important to us is the last line in their loop that says new sum equals new sum plus term. What that line does is it takes your previous answer from your previous time through the loop and adds the next term to it. So every time you go through this loop, you're going to just add another term. For example, if the after running through the loop, you have this, you get this 1 plus x is your new sum. To get the next new sum, you're going to replace that with that new sum plus the next term. Okay, so then as far as the computer is concerned, you're going to take 1 plus x squared over 2 factorial, add those, take that sum, and that becomes your new sum. And then you run through the loop again. All right, so running through the loop again, we have our new sum. And then this time through the loop, we're going to add to it the next term. And then this new sum plus this next term, x cubed over 3 factorial, becomes our new sum. You'll continue doing this. If you look at the condition for your while loop, you're going to keep going until your new sum is essentially equal to your old sum. In other words, you're going to keep going until you're adding something that doesn't really matter as far as the computer is concerned. For example, if I do x to the 100th over 100 factorial, since factorials grow much more quickly than polynomials, your denominator here is huge in comparison to your numerator. And so the further you go in this series, you're adding smaller and smaller numbers. And eventually, the computer is not going to be able to tell the difference between the old sum and the new sum. Because as far as the computer is concerned, you're basically just getting to the point where you're adding 0 over and over again. So the while loop is set up to where it stops whenever it reaches that point. Whenever it thinks that there's no difference between the old sum and new sum, it's going to stop and tell us the answer. Okay, so that's kind of the setup for this algorithm. All right, so again, look at that code. That code is our algorithm for implementing the Taylor series. All right. Now, something that's interesting, if you read the example, they say that this code works fine if x is greater than 0. So for any positive x values, they're saying that this will give us a good approximation to the true answer. So if I wanted to do e to the 10th power, I would do 1 plus 10 squared over 2 factorial plus 10 cubed over 3 factorial and keep going until eventually I'm not really adding anything significant. However, what they focus on is x being a negative number, in this case negative 20. So let's talk about what happens if we're doing x equals negative 20. So according to our Taylor series, e to the negative 20 is 1 minus 20. And then I'll have plus negative 20 squared over 2 factorial plus negative 20 cubed. Here, the negative number cubed, I'll just write this as a minus, and the 20 cubed over 3 factorial plus 20 to the 4th over 4 factorial, and so on. So again, at some point, and they actually give you a nice table on page 128 of the terms in this series, right around the, I believe, the 20th term, things start to kind of get under control. For a while, 20 squared, 20 cubed, 20 to the 4th, those are really huge numbers, and you end up with a really big number, but then eventually the factorials start to take over, and the answers should theoretically start to settle into the actual number. Now, if we're doing this in using our algorithm, it turns out, if you again read in the example, they say that the computed result from this algorithm is only accurate out to 8 decimal places. That's not very good when we're dealing with a computer with double precision that should be able to give us answers accurate out to 16 decimal places. So we've got half of the decimal place accuracy that we would want. All right, so we want to figure out what's going on here. Why are we getting an answer that's accurate only to 8 decimal places and not to 16 decimal places? Where is our error coming from? The first thing we might want to check is how's the conditioning of this problem? All right, so let's look real quick at the relative condition number for e to the x when x is negative 20. All right, so I'll just do a little scratch work on the side real quick. If I'm doing my relative condition number, kappa of x, that's absolute value of x times f prime over f. In this case, this is absolute value of x times the derivative of e to the x, which is e to the x, divided by e to the x. The e to the x's cancel, and we're left with just absolute value of x. So our relative condition number for this function e to the x is going to be equal to whatever the absolute value of whatever x value you're working with. So in this case, our relative condition number at negative 20 is absolute value negative 20, which is a relatively decent number. All right, we're not dealing with some huge relative condition number like a million. We don't want huge condition numbers. We want our condition numbers to be fairly small, and 20 is reasonably small. So our relative condition number is good. So that tells me that this function e to the x at negative 20 is well conditioned. We could look at the absolute condition number as well. That'd just be absolute value of e to the x. If I plug in negative 20, e to the negative 20 is a tiny number as well. So whichever type of condition number you want to look at, absolute condition or relative condition, we have a good answer. So in the end, our function e to the x at when x is negative 20 is well conditioned. Okay, so if the book is telling us that we run this algorithm for x equals negative 20 and we get an answer that's only accurate out to 8 decimal places, the problem doesn't lie with the function itself. The function itself at negative 20 is well conditioned. So now we need to think about where we could be running into issues with our algorithm. And just to kind of point out where I think the main issue is, it's exactly this line that I wrote down here, new sum equals new sum plus term. If you think about e to the negative 20, after you go so far in your series, let's say we go out to 100 terms again, that's going to be a number that's really close to e to the negative 20 if we do this analytically. E to the negative 20 is a tiny number, right? So this would be roughly equal to e to the negative 20 if we plugged in 20s everywhere we saw x's, or negative 20s, or no, negative 20 everywhere we see x's. And e to the negative 20 is a pretty small number. Now, if you think about our series, every other term in the series is a subtraction, right? Because whenever I do negative 20 raised to an odd power, I get a minus sign, and so my addition turns into subtraction. So eventually, I'm dealing with things like plus 20 to the 100th power over 100 factorial minus 20 to the 101st power over 101 factorial. Now think about what we have here. When we do this, new sum equals new sum plus term. If this whole thing here was our previous sum from the last time through the loop, and then we're subtracting off our next term, we know that our new sum out to, let's say, 100, we're dealing with something that's going to be pretty close to the actual answer for e to the negative 20 if this is done analytically. So this is going to be a pretty small number. And I'm subtracting off 20 to the 101st over 101 factorial. That is also a small number. And the operation that's happening between these small numbers is subtraction. Now think back to earlier in the video when we were doing the forward error analysis for floating point addition. We talked about how if we subtract numbers that are close to each other, then we could be introducing unnecessary round-off error. Okay, because that relative error, we'd be dividing by something close to 0, and we could be introducing round-off error there. So if you think about this series, every time we subtract off a number close to 0, and then subtract off another number close to 0, we're subtracting numbers that are close to each other. And subtracting numbers that are really close to each other could introduce this problem for us. All right, so this is why I think in the book they said that this algorithm works fine if x is positive. If x is positive, then every single one of these terms is just an addition. X is positive, so we're always adding. But if x is negative, then every other term is a subtraction, and eventually you're doing a whole bunch of subtractions of numbers that are close to each other, that every time we do that, it's introducing some round-off error. And then over time, if we go far enough and do this enough time, that round-off error is going to build up to the point where, like we see in the book, we've lost about half the accuracy that we would want. All right, so this is an unstable algorithm. The algorithm is unstable because this new sum plus term, if that turns into a subtraction on some of the steps and you're subtracting things that are close to each other, you could be introducing round-off error unnecessarily. The exercise that they give at the bottom of the page of 127, they say, how can you modify the above code to give you an accurate result? And this kind of answers that for us. They say e to the negative x is the same thing as 1 over e to the positive x. And we know that when x is positive, we don't have a problem. So one way we could fix this algorithm is instead of doing new sum equals new sum plus term for e to the negative 20, we could start by doing e to the 20, have the computer do that because the computer can handle positive exponents no problem. And then maybe once we have an answer for e to the 20th, we can do 1 divided by that answer to get e to the negative 20th. This is a way that we could take an algorithm that's unstable and fix it. So this really kind of highlights for us the difference between conditioning of problems and stability of algorithms. If there's a problem with the conditioning, what we're looking at down here, there's really not a way to fix that. It's just some fundamental flaw with the way the function is set up. There's certain x values where that function just is not well conditioned. An algorithm, on the other hand, if it's unstable, then you can look through the lines of your code and see if there are any places in that code that might be introducing error unnecessarily, and see if you can take a different approach to programming it so that you don't have that error, which is exactly what we're talking about up here. Instead of doing e to the negative 20, let's do e to the positive 20 and get that answer, because we can do e raised to positive numbers with this algorithm, and we're never doing this subtraction of numbers that are close to each other. All right, so we get e to the 20th power, and then do 1 divided by that to get e to the negative 20. So this avoids the thing that was causing our algorithm to be unstable, and now we have a stable algorithm that gives us a good result. So in this last example, we're going to look at how we can use a numerical approximation for the derivative of a function. We don't need to dig too deep into this example because it's covered in quite a bit of detail in chapter 9. So assuming we make it to chapter 9, like I'm hoping to, then we'll see a lot more of it there. But what we're doing here is we're approximating f prime of x with the difference quotient, f of x plus h minus f of x over h. And we know from calculus that that difference quotient is an approximation to the derivative for small h. Remember, the definition of the derivative is the limit of that difference quotient as h goes to 0. So there's two things we want to look at with this approximation to the derivative. One is truncation error and the other is round-off error. First, with truncation error, they show in the book that f prime of x can be written exactly, not as an estimate, but exactly as the difference quotient, f of x plus h minus f of x over h minus h over 2 times f double prime of psi. They do this using Taylor's theorem. You can look in the book on page 128. They take that equation using Taylor's theorem for f of x plus h, and then they rearrange that equation, solve it for f prime of x to get this expression I just wrote down. And here psi is some number between x and x plus h. So notice f prime of x is exactly equal to, according to Taylor's theorem, this expression here. Not an approximation, but exactly equal to this for some number psi between x and x plus h. So if we compare it to our estimate, just strictly based on the difference quotient itself, it's pretty clear where our error is. This piece right here tells us how far our difference quotient is from the actual derivative. This is what we call our truncation error. So the truncation error is this term at the end that shows for some number psi between x and x plus h, that number h over 2 times f double prime of psi is how far the difference quotient is from our actual answer. Notice here our truncation error is proportional to h. Okay, and remember, when we say proportional to h, we mean it's a multiple of h. So you could also think of this as being f double prime of psi over 2 times h. So our truncation error is proportional to h, or we say that it's of order h. Or we write it this way, a capital O, or big O, of h. So this means that the smaller h gets, the better our approximation will be. If our truncation error is a multiple of h, then if h is small, then we have a good approximation because our truncation error will also be small. Now on the flip side, let's look at the round-off error. They go through a little bit of explanation here. I don't want to really bother with the explanation they give there in the book, but where they end up is that our round-off error for the difference quotient is going to be about 2 times epsilon times f, or absolute value of f, divided by h. So your round-off error is proportional to 1 over h. So again, if we want to write this as a multiple of something in terms of h, this is 2 epsilon, absolute value of f, times 1 over h. So our round-off error is proportional to 1 over h. So in this case, as h gets small, our round-off error will get bigger. So there's kind of a balance that we have to find between our truncation error and our round-off error. If h is small, using this approximation of the difference quotient, if h is small, then the truncation error is small, but the round-off error could be large. On the flip side, if h is a little bit bigger, then you can make your round-off error decrease, but then your truncation error will increase. Okay, so this kind of interesting balancing act between truncation error and round-off error makes the difference quotient kind of have some issues as if we try to use that as our algorithm for the derivative, or approximating the derivative. Returning to that idea of conditioning of problems versus stability of algorithms, it's possible that you can have a problem that is well conditioned, and this algorithm, using the difference quotient to find the derivative, has unnecessary round-off error. So then what chapter 9 is going to focus on quite a bit will be, how do we come up with a better algorithm for approximating the derivative. One last thing I want to show you guys before we finish this video is I want to look at number 3 in your homework a little bit, because it looks like you would need to be focusing a lot on that last example to be able to answer this, but I really think you can get through this question really based more off of what we've seen in chapter 5 than what we talked about in the previous slide. So in this question here, they're asking us to approximate f prime of 1 for some function. Now they're not telling us what the function is, so we can't do anything too specific here, but if we're going to approximate f prime of 1, we know from the difference quotient that I would be doing f of 1 plus h minus f of 1 divided by h. And the idea is that the closer h gets to 0, the closer this quotient should be getting to our derivative. Now, something we did talk about in the last slide is we have this balancing act between our truncation error and our round-off error, and when we're dealing with computers, there's kind of a limit to how small we can make h. So something you'll need to think about here, what they're asking you to use for h is 2 to the negative 24th, and assume that you're working with a single precision computer. So if we're dealing with a single precision computer, remember our machine precision there is 2 to the negative 23rd. So really what this question is asking is, what happens when we make h smaller than what the machine can handle, right? Because what the smallest number the machine can handle here is 2 to the negative 23rd, but we're doing 1 plus 2 to the negative 24th. So really what this question boils down to is I want you to think about how the machine will handle this number here, and kind of base your answer to that homework question on what's happening to that 1 plus 2 to the negative 24th in a single precision machine.